Okay, so for ammonia, right, you will need to know what are reversible reactions and how to actually undergo creating or manufacturing ammonia using the Heber process, and also what are the uses of ammonia to develop into its salts content. So many chemical reactions, right, they are usually one way. However, there are some reactions that are two way, given different kind of conditions. So in JC, when you go up, you will learn things like Chandler's principle. But over here, how are we able to control the direction of the reaction for ammonia, right? It's either by pressure, temperature, or by the concentration of different reactants or products that you use here. So the forward reaction, right, is basically how you use nitrogen and hydrogen to form ammonia gas, whereas the backward one is how from ammonia gas you form your nitrogen and hydrogen. And what you do is you just draw a double arrow to show that this is actually a reversible reaction. So solid ammonium chloride, right, decompose upon heating to form ammonia gas and hydrogen chloride gas. Do take note, it's not hydrochloric acid, because over here you are forming the gas, and upon cooling, right, you actually form solid ammonium chloride. Okay, so this is also one reaction where you actually form your ammonium salt. So a reversible reaction can usually go forward and backward at the same time, and this is indicative by your double bond. So the reaction that moves from left to right in this direction, from here, the left side to the front, the right side, this is what we call the forward reaction. And then if it's from the product to form backwards, back to the reactants one, right, you will actually form the backward reaction. Okay. So manufacturing of ammonia by the Heber process, you must first know what are the conditions that are required for manufacturing ammonia. Number one, the raw materials, and in this case would be your nitrogen gas and hydrogen gas. Not H, neither is it just N. It is actually the gas. So how do you obtain this? You actually obtain it from fractional distillation of liquid air. You are not able to actually fractional distillate gaseous air. Okay, so how do you form it into liquid air? You first, under high pressure, compress it from gaseous state into the liquid state. Okay, so then from that you actually separate it out via fractional distillation. How to get hydrogen? In our organic chem chapter, we learned that you can actually undergo cracking, where you use long chain hydrocarbon with catalysts and high temperature and pressure. You are actually able to form hydrogen gas as well as your other smaller chain alkanes and alkenes. Okay, so the condition for this formation of ammonia using nitrogen and hydrogen is you use high pressure and high temperature with iron catalyst to help speed up reaction. But how high is the temperature, how high is the pressure, depends on the condition for the whole reaction to take place. Because too high of a temperature, you will actually cause out the catalyst to stop working. Too high pressure, the cost of maintaining the equipment will be expensive. So how to reach a balance to make sure that ammonia you get the maximum yield of ammonia. So this reaction between hydrogen and ammonia and this reaction between hydrogen and nitrogen to form ammonia is a reversible process, and some of this ammonia form can be reverted to nitrogen and hydrogen. So in order to maximize the yield, that means producing the most highest amount of ammonia at minimum cost, the reaction conditions have to be carefully controlled. How is the optimal pressure for the manufacture of ammonia being selected? Is where the higher the pressure, there will be a higher yield of ammonia. And this will then, higher pressure will also increase the speed of reaction in the chapter of speed of reaction. And this maintaining high pressure, and this will actually help to push the production yield. However, having high pressure is very costly because you need specialized equipment to contain the pressure. And at the same time, there is also a limit to the amount of pressure that can be actually applied. Secondly is optimum temperature. You use the same thing but you try at different temperature. And you realize that the lower the temperature, the yield will be of ammonia is higher. And this is because decomposition of ammonia into your hydrogen and nitrogen is also reduced due to basically maybe due to the catalyst or whatever reaction. As too high of a temperature may not be suitable as well. Second thing is that having low, but one of the draw for is having too low of a temperature, your reaction will be very slow because of the kinetic energy available for the speed of reaction. So what is a suitable temperature? So far they've done a lot of calculations and experiment. 450 degrees Celsius is one of them. Okay, so you use a catalyst so as to speed up the speed of reaction, but how so? So that you could see that your activation energy maybe initially needs very high temperature, but now you reduce the activation energy. Lower amount of temperature can help push the reaction. And of course, too high temperature, you need specialized equipment as well. So that's where the balancing comes into play again. So what are the operating conditions? Best condition is pressure at 250, temperature at 450. You use finely divided iron catalyst. Okay, why finely divided? So that you can actually increase the surface area for the catalyst to react, to help. Okay, so how is the whole Born-Haber cycle process done? You will need to follow the equation of N2 plus H2 give you NH3. So if you balance it out, okay, this is a reaction. For again, because all this is gas, right, it follows the mole, the Avogadro's constant ratio, where 1 mole of nitrogen requires 3 moles of hydrogen to give you 2 moles of ammonia. So if you have 1 dmq of nitrogen, you need 3 dmq of hydrogen to form 2 dmq of ammonia. Okay, so this is where we represent by volume, 1:3. So where we get the nitrogen is through liquid fractional distillation of liquid air, where liquid air you first compress it, become liquid, fractional distillation to remove the nitrogen, cracking helps to produce the hydrogen, send it down, nitrogen and hydrogen are then mixed in this ratio 1:3 so that you don't actually so that you don't let me think what I want to say. So that you don't actually put any wastage or in excess or put a limiting factor into it. So it's in 1:3. Then the mixture of the gas is actually compressed into 250 atm. Okay, the pressure, and of course you heat it up. So the gases are then heated up at 450 degrees Celsius and pass about finely divided iron over here. So these are the catalysts. Okay, and then the reaction is exothermic. So in case in MCQ they ask you, this one will result in an increase in temperature through the surrounding, and however only 10 to 15% of the nitrogen and hydrogen is converted to ammonia, where it's a gas, right? You want to cool it in this chamber here. So you condense it and then you slowly collect the gas. Second thing is, why do we have this particular segment here? It's so that any unreacted nitrogen or hydrogen can be passed on and then reused again. Okay, so any unused or unreacted nitrogen and hydrogen are then pumped back into the converter for further reaction. So you recycle it, you don't pass it out. So this ammonia gas in this segment, right, they are being condensed to form liquid ammonia in this way, and therefore we actually collect it. So a mixture of ammonia, nitrogen and hydrogen is then obtained, and therefore this mixture of gas is then cooled for storage. Lastly, we look at displacement. So whenever ammonium salt is heated with an alkali, this is in the chapter of acid and base, you see that ammonia would actually be able to be formed. So ammonia, how do you test for ammonia? is basically you will see a moist blue litmus paper turn red, right? Yeah, so that is the test for ammonia, and that some examples of ammonia salts are like your ammonium nitrate and ammonium sulfate. So this is ammonium chloride. So you would see they will form your sodium chloride, where these will be displaced with this. And your NH4 will be used to form your NH3 as well as the water. Okay, so that's the displacement reaction. Ammonium nitrate is NH4NO3. Ammonium sulfate is NH4SO4. Because sulfate is SO4 2 minus. Okay, crisscross. Okay, example of alkalis, you have your NaOH, very very popular one, and your calcium hydroxide. Okay, and generally, another thing to take note is there's a difference between ammonia gas and aqueous ammonia. Aqueous ammonia gas, right, is actually NH3. Aqueous ammonia is ammonia gas that has been dissolved in water to form your ammonium hydroxide, is NH4OH. Okay, so these are two separate things, especially in exam. So what we have covered is generally this. For ammonia, you need to know how to actually form ammonia through the Heber process. You require nitrogen and hydrogen in the volume of 1:3, and also how do you actually obtain nitrogen gas, and how do you obtain hydrogen gas, and lastly also for the purpose of ammonium salt, how do you actually form ammonium salt, okay, where ammonia gas can also be released.